Okay guys, so this video is a follow-on from a previous video where I showed how to graph basic sine and cos graphs. Decided to put this on because I know quite a few students have issues with both translations of sine and cos graphs and also graphing tan graphs. So we're going to start off with looking at a basic tan graph and why a basic tan graph is or looks how it looks. So I've drawn by hand both sine and cos here. I probably should have labeled them so you know which one's which. This one here is cos x, and the blue one is sine x. I have drawn them between negative 2 pi and pi, 2 pi and 2 pi, just so negative 2 pi and 2 pi, just so you can get the idea of what tan looks like. In regard to tan doesn't have an amplitude. So it's different to sine and cos. And another thing is, tan's period, it isn't 2 pi on n, it's pi on n. Okay, so that's the time it takes to complete a tan graph. It is pi on n. Tan doesn't have an amplitude. You can have a dilation factor with tan from the x-axis. However, the amplitude, like if they ask for the amplitude, it simply doesn't have an amplitude. Okay, one of the things I wanted to remember is that tan x is equal to sine x on cos x. And that's why I've drawn the graph of sine x and cos x here, because I wanted you to basically draw a parallel between sine and cos x and tan x. And I'm going to go for something bright so that you can hopefully see it. So we want to have a look at our blue graph and our green graph, and from that we want to create our pink graph, which is tan. So to start us off, we know that tan is sine x on cos x, so let's use that. We know when x equals 0, sine is equal to 0, and cos is equal to 1. So if I did 0 over 1, I would get 0. So the first thing we know is it goes through 0. Okay, next thing, if we have a look here at pi on 4, sine of pi on 4 is root 2 on 2. Tan of pi on 4, cos of pi on 4, that's also root 2 on 2. What happens when you divide something by itself? You get 1. So at this point here at pi on, that should have been a pi on 4, not a pi on 2. Pi on 4, we get sine on cos, which in this case, these two values here, if we divide them by themselves, we get 1. So at pi on 4, tan, in this case, equals 1. Okay, what about when we get to pi on 2? Really should stop putting those dots there. Okay, so I've got sine, which in this case is 1, divided by cos, which is 0. What is 1 divided by 0? We can't do it. It's undefined. So we have to label that with an asymptote. So x equals pi on 2 is undefined. Okay, now we'll go backwards and we'll have a look and we'll see. If I have cos of negative pi on 4 and sine of negative pi on 4, they're the same value, but cos is positive and sine is negative. Now, if I have a negative divided by a positive, I'm going to end up with a negative. So here, negative pi on 4 is going to be negative 1, because I've got the same number, but one's positive and one's negative. When we move to negative pi on 2, which is what we got here, if I have sine, which is the blue, divided by the green, negative 1 divided by 0, once again, we have a value that's undefined. So, at this point here, we get x equals negative pi on 2. That's also undefined. Now this distance here to here is from negative pi on 2 to pi on 2. That's pi, which is what the period of tan is. In this case, it's pi on 1. So our period is pi in this case. Now, what does the graph look like everywhere else? Well, if I have, let's think about in here, like this area here. If I have blue, which is sine, divided by cos, if I have a number that's about 1, and I divide it by a smaller number, we get a bigger number. So if I said for here instance, if I had 1 divided by, my green graph might be a third, that's going to equal 3. So here that's going to go up to somewhere higher. So this graph, tan graph, looks like that. So it approaches the asymptote, going to infinity. Oops. Doesn't ever get there. And then down here, it's actually going to become negative. And once again, it's going to approach the asymptote. So that is our one basic graph of sine. You'll notice here, at the halfway point between the x-intercept and the asymptote, i.e. in this case pi on 4, it goes through 1. Whatever the coefficient of tan is, that is where it will go through halfway between the x-intercept and the asymptote. Okay, now that's assuming that we don't have any translations left and right or up and down. Okay, so we've got one basic graph. Let's do the same thing again. Here, if I've got sine, which is a large number, or not large, but it's positive, divided by a really small negative number, a positive number divided by a really small negative number is a really big negative number, so it's going to be negative. Once again, at this value here, 3 pi and 4, they're both going to have exactly the same value. The only difference is one of them is negative and one of them is positive. So if we divide a negative and a positive with the same value, that's going to be negative 1. At this point here at pi, sine is 0 and cos is negative 1. So if I say, what's 0, how many negative 1s? It's 0. So a graph we know looks like that. Probably doesn't curve as much as what I want it to. Okay, as we move on, I've got two negative numbers here at 5 pi and 4. When I divide two negative numbers together that are the same, I get positive 1. So if I had negative 2 on negative 2, I'd get 1. Here, I've got negative 1 on root 2 divided by negative 1 on root 2, I get 1. Okay, and then once again here at 3 pi on 2, we're going to have sine, which is negative 1, divided by cos, which is 0. We can't do that because you can't divide by 0. So in this case here, we get another asymptote. And that makes sense because we've moved pi across. And every pi, we have a new graph. Okay, so there's our graph of tan. Probably doesn't look as good as what it should, but you get the idea. Okay, so you can see a pattern that occurs. Here, if I move across, it's going to go through that value there at negative 1. It's also going to go through at 0. And our sketch is going to look something like that. We know that's going to be the point 2 pi 0. If we go backwards, we know that if you have a look at our asymptotes, they're coming every pi, which is our period, which makes sense. So if I go back from negative pi and 2 back to negative 3 pi and 2, so x equals negative 3 pi and 2, then we know at the halfway between the asymptotes, it always goes through the x-intercept. Here I've got two negative numbers that are the same. When I divide them together, I get positive 1. So our curve's going to look something like the same thing as the other ones. I'm going to get negative 1 here. Oops. So let's say about here. And then my graph's going to look, oops, it's a bit dodgy. Should approach that asymptote. Okay, and then we got one more graph. Halfway between these, it's going to go through positive 1, it's going to go through 0, so it's going to look like a bit dodgy again. Okay, so there's our graph of tan from negative 2 pi to pi. Now, in short, I'm just going to do a breakdown here. Our period for tan, actually let's write y equals tan and a tan and x. Okay, so our period is pi on n. Now our asymptotes, our first asymptote is always a half of the period. So it's going to be pi on 2n. Your next asymptote, you just add the period. This is for a graph that hasn't been translated up and down. X-intercepts occur halfway, between asymptotes. And assuming it hasn't been moved up and down, A is the y value halfway, I should say plus or minus A, halfway between the x-intercept and the asymptote. Sometimes I call it the halfway mark. Okay, so our period's pi on n. Our first asymptote is pi on 2n. The next asymptote, we just add our period. The x-intercepts occur halfway between the asymptotes. Plus or minus a is the y value halfway between the x-intercept and the asymptote. Now, let's have a look and see if we can apply it to this. So, we want to sketch a graph. We want it between negative 2 pi and 2 pi. Now, remember, it doesn't have an amplitude. So I'm going to say my halfway mark y is equal to 2 because we've got this dilation factor 2 from the x-axis. Okay, so my halfway mark y equals 2. My period is still pi because it's pi on n, which is just pi because there's a 1 out the front. Okay, my first asymptote would be pi on 2. However, this graph is translated right pi on 4. So we can see our first asymptote, because that affects the translation affects our asymptotes. Our first asymptote is pi on 2 plus pi on 4, which is 2 pi on 4 plus pi on 4, which is 3 pi on 4. Okay, so we know when our first asymptote is. We can say when our second one is. We just add our period. So 3 pi on 4 plus 4 pi on 4. That gives us 7 pi on 4. If we add another asymptote on, we're going to go outside the domain, because if you think about these, if you put them on pi on 4s, that's going to be 8 pi on 4 and negative 8 pi on 4. Okay, so we can go backwards to get our asymptotes, but I'll just do it all as we work through the question. So the first thing I'm going to do is draw an axis. That's really bad. So this is my y-axis. My x-axis. Now we need to go between negative 2 pi and 2 pi. So let's say there's 2 pi, there's pi, there's negative pi, negative 2 pi, and we know everything is going to have something to do with a pi on 4. So let's cut it all up into pi on 4s. That's pi. Oh, that might be a little bit dodgy there. I might need to move this one out a bit more. Okay. So they're all pi's on 4s, negative 2 pi, negative pi. Okay, we know our first asymptote. Let's change colour, we'll go with this purpley blue. Our first asymptote occurs at 3 pi on 4. So once you get your asymptotes in, these things become really easy. Now, don't forget, you've got to label an asymptote. X equals 3 pi on 4. Our next one is at 7 pi on 4. So as you can see, x equals 7 pi on 4. We've got to go back 1, 2, 3, 4 notches to get our next asymptote, which is going to be x equals negative pi on 4. And then if we go back 4 again, we get negative 5 pi on 4, x equals, because they're asymptotes, you have to label them with an equation. Okay, now it hasn't been reflected in the x-axis. If there was a negative out the front, it would turn the graph upside down, but it hasn't. So we've got all of our asymptotes in, and our period we've taken into account. Our halfway mark is 2. So let's see on our graph, there's 2, and there's, negative 2. Okay, so we've pretty much got everything in place now. We know that our axis intercept always occurs halfway between the asymptotes. So halfway between the asymptotes is here. We know that the halfway point is 2 and negative 2. So our graph is going to look like that. Halfway point, halfway point, halfway point. So we've got 2 halfway points. We've got a halfway point between the asymptotes, and then we should call them quarter points. Same here. Now this is going to be negative 1, just because there's only a quarter of a graph there. So we know that's 2 pi, negative 2. Halfway point, quarter point, quarter point. There's our graph. Halfway point, quarter point. So remember, it's got no amplitude, but it's been dilated by a factor of 2 from the x-axis. So there's our graph. Looks pretty good if I do say so myself. Okay, so we've got, because we're between negative pi and 2 pi, negative 2 pi and pi, and we know that in this case, our period was pi, we should see 4 graphs in total. We have got 1, 2, 3. This little bit and this little bit here make up 4 graphs. So that's how you graph a tan graph. You get the period, first asymptote. If it's translated left or right, then you simply move the asymptote left or right. Get your next asymptote by adding the period. Go backwards by subtracting the period. Once you've got all your asymptotes in, your x-intercept is the halfway mark. And then your quarter way mark is the value of a, which is the coefficient of the tan function. Okay, so hopefully that's helped with graphing a tan graph. Okay, here we have another tan graph. Let's write all of our information down. Okay, my dilation factor is 1, because it hasn't been dilated anywhere. My first asymptote, oops, what did I forget? I forgot my period. My period in this case is pi on n, which is 2, so it's a bit different. Oh, this one looks like it's a bit nasty because this is on 2 and our translation's on 3. But let's have a look. My first asymptote would be pi on 4 because it's a half the period. However, it's been translated right, right, pi on 3. Therefore, first asymptote is pi on 4 plus pi on 3, which is, let's put them over a common factor of 12. So 3 pi on 12 plus 4 pi on 12, which is 7 pi on 12. So first asymptote is 7 pi on 12. To get to our next one, if we add the period. Now, if these are going to be on 12, we're going to get negative 12 pi on 12 to 12 pi on 12. So if we add our period, we got 7 pi on 12 plus pi on 2. But pi on 2 is 6 pi on 12. So plus 6 pi on 12, that's 13 pi on 12. That's not in our domain, so we don't have to worry about that one. So we get our previous asymptote. We subtract the period. So 7 pi on 12 minus 6 pi on 12 is pi on 12. Okay, so we've got an asymptote at 7 pi on 12, we've got an asymptote at pi on 12. Let's start graphing it because it'll make it easier. Once we've got two asymptotes in, everything else becomes easier. We want it between negative 12 pi on 12 and 12 pi on 12. So there's our y-axis. Our x-axis. Okay, so let's say that's pi, and that's negative pi. And the way I do it, split it in the middle, split it in the middle, split it again, and again, and again. And then each one of these is going to have 3 notches because we want it to be 12. And then here, 1, 2, 1, 2, 1, 2, 1, 2. So they're all pi on 12s. Now we have an asymptote at pi on 12 and at 7 pi on 12. So let's have a look. Pi on 12 we know is here. So x equals pi on 12. My next one, 1, 2, 3, 4, 5, 6, 7. So x equals 7 pi on 12. Okay, we've got to go back 1, 2, 3, 4, 5, 6, because that's when our next asymptote occurs, because our period is 6 pi on 12. So negative 5 pi on 12. Then if we go back 6 again, we're going to go to negative 11. Don't forget it's a label, x equals negative 11 pi on 12. Okay, now that we've got our asymptotes in, and it hasn't been reflected in the x-axis, we can simply halfway between the x asymptote, so it's our x-intercept. Now it goes through 1 and negative 1. So our quarter way mark halfway between those is going to be 1, quarter way mark, negative 1. That last bit's a bit dodgy. So down, halfway, quarter way, quarter way. Halfway, quarter way. Don't know exactly where that is. We could sub pi into the equation to work out what it's going to be. I'll do that in a sec. Okay, halfway between those is there. Halfway, halfway. And wherever we finished off over there, we're going to start off over here and go up, because together this bit and this bit would make a full graph. Now, if we wanted to find when x equals pi, we get tan 2 pi minus pi on 3, which is tan 2 pi on 3, which is tan of 4 pi on 3. Now we know that's going to put us into the third quadrant where tan's positive. So that's exactly the same as tan of pi on 3. Okay, we can work out what tan of pi on 3 is from our special triangles. 1, 2, root 3. There is pi on 3. So tan of pi on 3 is root 3 on 1. So this value here is root 3, which is 1.7. So it probably shouldn't be up that high. Let's say it's here. Oops. So pi root 3. This value here is going to be 0 root 3. And this value here is going to be negative pi, positive root 3. We also know our x-intercepts. 1, 2, 3, 4 pi on 12, which is pi on 3. 5, 6, 7, 8, 9, 10 pi on 12, which is 5 pi on 6. Back here, negative 2 pi on 12 or negative pi on 6. Negative 2, 3, 4, 5, 6, 7, 8. Negative 8 pi on 12, which is, divide them both by 4, negative 2 pi on 3. So there is our tan graph from negative pi to pi with a translation pi on 3 to the right, and it has a period of pi on 2. Okay, now we're going to look at sine graphs with those nasty translations. Everyone seems to hate this, but if you use the chunk method, it'll make sure that you know what you're doing. Okay, so with our chunk method from previous, if you haven't watched the video, make sure you go back and watch it. Don't forget to like, share, subscribe, and something about notifications, whatever they say. Okay, So let's start. We've got an amplitude of 2. Our center is at 0, so our max is 2, and our min is -2. Our period is 2 pi on 2, which is pi. Oops, don't know what I did then, but I flicked the screen. Okay, so 2 pi on 2, which is pi. Now remember, a chunk is a quarter of the period, so it's pi on 4. And in this case here, we have a translation of pi on 3 to the right. Okay, so pi on 3. Now, if you look, our period, our chunk, and our translation, they're not friends because they're all on different denominators. So what we want to do is get them all on the same denominator, so it makes it really easy to graph. So a friendly thing for pi on 4, pi on 3, and pi is 12. So 12 pi on 12. If I put that on 12, I get 3 pi on 12. If I put that on 12, I get 4 pi on 12. So now we can say it's translated 4 pi on 12 right. Each chunk is 3 pi on 12, and one period is 12 pi on 12. Now I deliberately made this hard to do. We want to sketch from -pi to 2 pi. So I'm going to make it a big graph, hopefully. I've got to go up and down 2. Okay, oops, so let's go. It wasn't very straight, but luckily the program fixes it for me. Okay, so I want to go from -pi to 2 pi. Okay, so let's say here's -pi. Oops, that line's not very straight at all. Okay, that's better. -pi, we want to go the same distance, pi, 2 pi. We want to go up to 2, want to go down to -2. Now we know we've got to cut them up into pi on 12s, so that's where the fun begins. I'm going to make this thin because when we cut them up, that, cut it into 2, then into 4, now into 12. 2, 4, 12, 2, 4. Hopefully if they ever got you to graph a graph like this, they would actually have a scale on it, which will make it much easier. Okay, so it's a sine graph, which starts in the center. We know it's been translated 4 pi on 12 to the right, so that's our starting point. So if we go 1, 2, 3, 4 pi on 12 to the right, now we can forget about our translation. We've taken that into account. It's a sine graph, and we know every chunk we go up or down. So every 3 pi on 12 we go up or down. So here, as I go to the right, 1, 2, 3, I go up. 1, 2, 3, because we know a sine graph goes up first, down. 1, 2, 3, we go down. 1, 2, 3, we go up. 1, 2, 3, we go up. 1, 2, 3, we go down. If we go back, 1, 2, 3, we go down. 1, 2, 3, we go up. 1, 2, 3, we go up. 1, 2, 3, down. 1, 2, 3, down. Okay, so our graph's going to look something like that, Okay, now the good thing is we know all of our intercepts and turning points because of our chunk method. We know this point here is pi on 12, negative 2. This one here, 1, 2, 3, 4, 5, 6, 7. 7 pi on 12, 2. Then we're going to go 6 more across, so we get 13 pi on 12, negative 2. We go 6 again, 19 pi on 12, 2. Our endpoints we'll work out in a sec. This one here, 1, 2, 3, 4, 5, negative 5 pi on 12, 2. Okay, we can also say our x-intercepts because we have 4 pi on 12 or pi on 3, 5, 6, 7, 8, 9, 10 pi on 12, which is 5 pi on 6, 11, 12, 13, 14, 15, 16 pi on 12, which we know is 4 pi on 3, 17, 18, 19, 20, 21, 22, 22 pi on 12, which is 11 pi on 6. If we go back, negative 2 pi on 12, which is negative pi on 6. Negative 8 pi on 12, which is negative 4 pi, no, negative 8 pi on 12. Divide them both by 4, negative 2 pi on 3. Now, if we want our endpoint, it's going to be the same at the ends and in the y-intercept. So a y-intercept, if we let x equals 0, we get y equals 2 sine 2, 0 minus pi on 3, which is 2 sine negative 2 pi on 3. Now if we go negative 2 pi on 3, we're going to be in the third quadrant where sine is negative. So we can say this is negative 2 sine of pi on 3. Of course, sine of pi on 3, 1, 2, root 3, is root 3 on 2. So it's negative 2 times root 3 on 2, which is negative root 3. So this value here is 2 pi, negative root 3, 0, negative root 3, and this last bit here, negative pi, negative root 3. And there is a complete translated sine graph using the chunk method with all of our x-intercepts, our turning points, and our endpoints without too much fuss. It's kind of nice. Can't remember how many examples I did. Okay, so we're nearly there. Okay, now we've got a cos graph. So let's see how quick we can do this one. We have an amplitude, which is 2. A center, which is 0, so our max is 2. Our min is negative 2. Our period is nasty, 2 pi on 3. A chunk is therefore 2 pi on 2 times 3, which is pi on 3. Is that right? No, I times it by 2 when I was supposed to times it by 4, because a chunk is divided by 4. So 2 pi on 4 times 3, they're going to cancel. I'm going to end it with a 2, so pi on 6. And our translation is pi on 4 to the right. Okay, so let's all change them into our magical chunks. Well, the same denominator. I've got a 3, I've got a 6 and a 4, so let's go with 12 again. So I'm going to get 8 pi on 12. I'm going to get 2 pi on 12, and I'm going to get 3 pi on 12. Okay, so we want to go from 0 to 2 pi. We know all of our information now. So, because it's going to be on 12, let's try and make it pretty wide as well. So we go from, it's bad, but we can straighten it up. And across. Alright, Okay, so we want to go up to 2, down to -2. Taking that into account, we want to go up until 2 pi and a halfway mark. Not quite, it's probably closer to here. Okay, so there's pi. Cut it in half, cut it in half, cut it in. So now they're in quarters. Now they're in twelfths. Okay, what do we know? Our graph has been moved 3 pi and 12 to the right. So we start at 3 pi and 12. We know every 2 pi and 12 we've got to do something, and it is a, oops, I stuffed it up. It's a cos graph, so it starts up the top. So every 2 pi and 12 we've got to do something. So 2 pi and 12, 2 pi and 12, 2 pi and 12, 2 pi and 12. Same again, and again, and again. If we go backwards, 2 pi and 12, okay, so, oops, that's a bit dodgy. It's harder to do when they're right next to each other. Of course, we know what our X-intercepts are. Okay, so that is 3 pi and 12, which is pi and 4, 2, 4, 5, 6, 7 pi and 12. That's right, isn't it? 4, 5, 6, 7, -2. 9, 11 pi and 12. Did I stuff that one up? That's 3 pi and 12, which is pi and 4. That's right. Okay, 2. We're going to go across 4, so 15 pi and 12, which is 5 pi and 4. -2. This one here, 15, 19 pi and 12. 2. This one here is going to be 23 pi and 12. -2. Okay, pi on 12. Oops. Pi on 12. 5 pi on 12. That one's going to be 5, 6, 7, 8, 9 pi and 12, which is 3 pi and 4. 8, 10, 11, 12, 13 pi and 12. Add 4, 17 pi and 12. Add 4, 21 pi and 12, which, if I can divide them both by 3, is 7 pi and 4. 4, not 12. Okay, if we let x equals 0, we get y equals 2 cos 3 times -pi and 4, which is 2 cos -3 pi and 4, which, if we sketch that, goes into the third quadrant where cos is negative. So it's -2 cos of pi and 4. Of course, we know cos of pi and 4 is 1 on root 2 from the special triangle, 1, 1, root 2. So it's going to be -2 times root 2 on 2, which is root 2. So this value here is 2 pi root 2, and then this value here is the same value, but at 0, root 2. Okay, so there's our graph of 2 cos 3x minus pi and 4 for 0 to 2 pi. And we've got a 3 out the front. That tells us how many graphs we should do between 0 and 2 pi. And you can see here we've got 3 full graphs, because that section and this last graph, together they make a full graph. Okay. Now, sorry if I'm making you feel sick. Okay, now this graph, oof, got a nasty one to end it off. Okay, so let's write everything down. Our amp is 2. Our center is -1. Our max is -1 plus 2, which is 1. Our min is -1 minus 2, which is -3. So we've got our range. Our period is 2 pi on 2, which is pi. That's not too bad. Our chunk is pi on 4, which is nasty with our translation. We have 2 translations. Translated right, pi on 3, down, -1. However, we've taken that -1 down into account here, don't forget. Okay, so let's put it all into our nice chunks. Seems to all be pi on 12s at the moment. Pi on, whoops, 12 pi on 12, 3 pi on 12, 4 pi on 12. Okay, so we've got a sketch from -pi to 2 pi. We've got all of the information that we need. So let's create our graph. Okay, so -pi to 2 pi. Now what's our max? Our max is 1, our min's -3. So it's got to be moved down a bit. Oops, let's go a little bit longer. That's better. Okay, so we want to go from -pi to pi, and then to 2 pi. Now they all have to be cut up into pi on 12s. So cut it in the middle, in the middle, in the middle. That wasn't quite. Then each one of those into 3. Because 4 3s is, the last two are a bit dodgy. Okay, they're all pi on 12s. We want to go up to 1. We want our center to be at -1. But we've got to go down to -3. We know that's pi. We know that it is a cos graph, so it starts up the top. And it is... Okay, so we've taken that into account. We know that it starts right, 4 pi on 12, and it starts at the top. So we go across 1, 2, 3, 4 pi on 12, and it starts at the top. We need to change our color. Let's go pink. 4 pi on 12, it starts at 1. Now every chunk, 3 pi on 12, is when at 1, 2, 3, it's going to go down to the center. And then 1, 2, 3, it's going to go to our minimum. Then another 1, 2, 3, center. Another 1, 2, 3, maximum. 1, 2, 3, center. 1, 2, 3, minimum. Okay. Now if we go back 1, 2, 3, we've got to be at our center. And then if we go back 1, 2, 3 again, oops, got to be at our minimum. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, I think we've got a good grasp on this graph. So, oops, that was bad. Got a feeling the bottom might be lower than what the top goes, but that doesn't matter. Okay, now we've got our turning point, so let's put them in. That is 4 pi on 12, which is pi on 3, 1. When we go across, that's going to be 10 pi on 12, which is 5 pi on 6, negative 3. This one here is going to be 11, 12, 13, 14 pi on 12, which we know is 7 pi on 6, 1. And then we're going to go across, what do we say, 14. That one's going to be 22. Is that right? 14, 15, 16, 17, 18, 19, 20. 20 pi on 12, 22, 24. Okay, so 20 pi on 12, which divided by 5 pi on 20 divided by 4 is 3. Negative 3. Okay, if we go back, negative 2 pi on 12, which is negative pi on 6, negative 3. 3, 4, 5, 6, 7, 8. Negative 8 pi on 12, which is negative divided both by 4, 2 pi on 3. Okay, so I've got all of our turning points. Let's get our y-intercept. So 2 cos 2 x minus 2 cos 2 x minus pi on 3 minus 1 x equals 0. We get 2 cos 2 negative 2 pi on 3 minus 1. Negative 2 pi on 3 is going to put us into the third quadrant where cos is negative. So negative 2 times cos of pi on 3 is a half. So negative 2 times a half, then minus 1, which is negative 2. So that looks like it's negative 2, and it actually is 0, negative 2. The endpoint here will be negative pi, negative 2. The endpoint here will be 2 pi, negative 2. Okay, I've got to say this graph looks pretty good. The only thing we need now is our x-intercepts. Now, in this graph, we can easily find them. I know it looks like it goes through certain values, but let's check and make sure. So, we've got 2 cos 2 x minus pi on 3 minus 1 equals 0. That gives us cos 2x minus 2 pi on 3 equals 1/2. So, cos inverse of a half is pi on 3. So I've got 2x minus 2 pi on 3 is equal to. Now I said pi on 3. When's the next time cos is positive? It's in the first and last quadrants. So it's in the last, around there is 5 pi on 3. If we need to go backwards, because we're going to the left of 0, we've got to subtract our period, which in this case, because it's on 3, it's going to be 6 pi on 3. So if I subtract 6 pi on 3 from 5 pi on 3, I get negative pi on 3. If I subtract 6 pi on 3 from pi on 3, I get negative 5 pi on 3. And then we've got to go forwards as well, so we've got to add 6 pi on 3, so I get 7 pi on 3. And then I get, if I add 6 pi on 3, 13 pi on 3. Okay, then we've got to add 2 to all of our solutions. So 2x equals negative 5 pi on 3. It's going to be negative 3 pi on 3. If we add 2, I get pi on 3. If I add 2, I get 3 pi on 3. If I add 2, I get 7 pi on 3. If I add 2, I get 9 pi on 3. If I add 2, I get 15 pi on 3. Okay, now we divide through by 2. So I get x equals negative pi on 2, pi on 6, pi on 2, 7 pi on 6, 9 pi on 6, which is 3 pi on 2, and 15 pi on 6, which is 5 pi on 2. Okay, so that value there, it looks like it, and it is negative pi on 2. My next value is pi on 6, which is 2 pi on 12, so we know that's right. 3, 4, 5, 6 pi on 12, which is pi on 2, so we know that's right. The next one is 7 pi on 6, which is 14 pi on 12, so that's right. 15, 16, 17, 18 pi on 12, which we know is 3 pi on 2, so that's right. 5 pi on 2 is bigger than 2 pi. However, here, if we go back 4 notches, that's negative 6 pi on 12, 7, 8, 9, 10, negative 10 pi on 12, which is negative 10 pi on 12 is negative 5 pi on 6. And there you are, we have our graph, including turning points. We know where the center is, we know where the minimums are, the maximums, and our endpoints. So hopefully now you'll know how to graph sine, cos, and tan graphs efficiently, including those really hard ones that suck. Hopefully you won't have to do any in the exam, but it's always good to know how to do them, and it's always good to know how to do the chunk method. My graphs look pretty good, I reckon. Okay, thanks for watching. Don't forget to like, share, subscribe,